share the link for the recorded version in the e-learning. Okay. So for those who want to do a revision for our last topic, so you can browse to the e-learning and then click the link. Okay, then you can get the lecture. Okay, which I uploaded in the YouTube. Okay. So same to today class. Okay. Inshallah, I will try to upload as early as I could. Okay. Because with a limited data mobile, so I need to enter to UTM. Okay. To upload for the for the recorded class. Okay. Okay. So for today, we may learn on how to analyze the stability of the infinite slopes. Okay. So for the first half class, okay, we may go through for the theoretical part. Okay. Then later on, we may discuss on some or several example. Okay. In terms of how to calculate or how to determine the factor safety for the infinite slopes. Okay. So as a refresh from what we learned last week, okay. So civil engineers often are expected to make calculation to check the safety of natural slope, slope of excavation and compacted embankment. Okay. So in the first point, okay, so we may deal with the natural slope, okay, but normally when we do some development, okay, we may disturb the slope. Okay, either we do a cutting, okay, or we may make a fill, okay, make a filling, okay, to increase the height of the level, okay. So we need to determine or to check for the stability of the slope. Okay. So slope of excavations. Okay. In that case, we check the stability in terms of the cutting process. Okay. And slope due to compacted embankment. Okay. So our rule is to determine what will be the stability for the for the filling or for the compacted structure. Okay. So these checks involve determining the shear stress developed along the most likely rupture surface and comparing it with the shear strength of the soil. Okay, as we have discussed previously. Okay. So there will be two type of force. Okay. For the first one, is the shear stress, okay, where this force, where there is a force of we call as a driving force, okay, which tend to make the block or the mass of the slope, okay, to moving downwards, okay. And at the same time, okay, there will be a resisting force, okay, which is governed from the shear strength of the soil itself. Okay. So in order to ensure the stability of the slope structure, okay, so definitely the resisting force should greater than the driving force. Okay. So this process is called slope stability analysis. Okay. Because we are using the limit equilibrium approach, okay, so we need to make sure that the driving force is less compared to the resisting force. Okay, if both of the force is same, so we can consider it is under a critical conditions. Okay. So the most likely rupture surface is the critical surface that has the minimum factor of safety. Okay. So our role is to determine the stability, okay, by assuming there there is a rupture surface, okay, developed, okay, on the slope, inside the slope structure. Okay. So by knowing the rupture surface, okay, so then we can start to use the properties of the soil, okay, in the calculations, okay, and then we also should include what we call as the groundwater level, okay, that might contribute to the driving force, okay, and would make the slope, okay, become less safe. Okay? So we need to include the effect from the what we call as the groundwater level as well. Okay. Okay, this is based on simple analogy. Okay, where we have a block. Okay, I guess I have discussed previously. Okay, on our first class. Okay, so we just imagine this block will move towards down. Okay, due to the due to the slope degree. Okay, so then we need to calculate, okay, what will be the driving force and also what is the resisting force. Okay, actually this is a new, not n. Okay. So the items that contribute to the driving to the resisting force is the weight, is the normal stress, okay, and also the the frictions, okay, which is develops on the rupture surface, okay, while the driving force is governed from the parallel force, okay, acting on the rupture surface. Okay. Okay. The factor safety FS for the transitional slip is defined as, okay, FR is the resisting force, FD is the driving force. Okay. So nu W cos theta, okay, over W sin theta, okay, is equal to the tangent of the phi, okay, over the tangent of the theta. Okay. Clearly, when the dipping angle theta is smaller than the angle of friction, okay, the resisting force Fr is greater than the driving force. Okay, so in this part, okay, we may discuss later on how they get the tangent phi and the tangent theta. Okay, actually, it is based on the shear strength or the more column model. Okay. So the resistive force Fr is greater than the driving force Fd, and the factor 1 and the factor safety is greater than 1, and vice versa. Okay. So when Fs is more than 1, so as we have discussed previously, it is under a safe conditions whereby 1.5 is the factor safety that we should use, okay, for the man-made slope, okay, while 1.2 to 1.4 is the factor safety that we should use for the what we call as the natural slope. Okay, so factor safety equal to 1, okay, is onset of failure, okay, or it is under critical condition. Okay, and then definitely if factor safety is less than 1, so we can consider it is under a fail situations. Okay, so in a simple determination, okay, so when we know that the phi is higher than the theta, or the friction angle is greater than theta, so we can assume that the slope it is under a safe conditions. Okay, but further investigation should be carried out. Okay, for example, by using any numerical tools. Okay, to confirm our first judgment. Okay. Okay. So the task of the engineer charged with the analyzing slope stability in to determine the factor safety. Okay. Generally, the factor safety is defined as Fs equal to tau F over tau D. Okay, where F uh, is the average shear strength. Okay, while for the average shear stress, tau D develop along the potential failure surface. Okay. So we have the F and O and D. Okay. So then the Fs has a part a ratio between C over CD, and also the Fs has a some part where it is called as a F phi, okay, which is tangent phi over tangent phi D. Okay. So Fs equal to Fsc and SFP. Okay. So when Fs is equal to 1, okay, the slope is in a state of impending failure. Okay. Generally, a value of 1.5 for the factor safety with respect to the strength is acceptable for the design of a slope, of a stable slope. Okay. So once, okay, it state of impending failure, or it uh, near to a failure conditions, okay, so it is better to use 1.5, okay, for the factor safety with respect to the strength. Okay. So this approach, okay, we may use for the linear methods. Okay, there will be another methods. Okay, where they use the concept of Fs, Fc, and Sv. Okay, to determine the failure safety, the factor safety for a finite slopes. Okay, by using the linear approach methods. Okay, so we may discuss later. Okay, on the finite slopes. Okay, where we may use the Fc and Fe. Okay, in determine the factor safety value. Okay. So method of analysis. Okay, so we have two type of methods. Okay, as I told you previously, we have a linear methods. Okay, so relatively simple. Okay, where these linear methods, okay, we may use in to conduct for the stability analysis for the infinite slope. Okay, where we will learn later. Okay, so we have another approach. Okay, where we deal with finite slope. Okay, where we use the linear failure plane approach. Okay, as I told you that we use the FSC, FSV in the approach. Okay, so analysis for the case of uh, for the phi u, okay, which is undrained condition. Okay. And there will be another approach on the wedge failure analysis, okay, where I will not discuss in this subject, okay, because it is more related to the rock slopes conditions. Okay. So for the nonlinear methods, okay, normally for these nonlinear methods is apply for the finite slope, okay, where we use several methods where we call as a method of slices. Okay. So it can be used for irregular slope geometry, okay, non-uniform soil conditions, and where we have a seepage in the soil. Okay. So it is a very useful tool, okay, to determine the factor safety, okay, for the finite slope, okay, but it is very a tedious approach, okay, where we need to spend a lot of time, okay, to conduct for this non-linear method analysis. Okay. However, okay, with the current development of numerical tools or software, so we can easily, okay, conduct for more than 2,000, for example, analysis within just less than 1 minute. Okay. Okay, on this particular subject, okay, we may learn manually, okay, on how to analyze the result based on the method of slices. Okay. So there will be two examples, okay, that I will provide. Where the first one is the methods that has been proposed by Fillenius, and another one is method that is being proposed by Bishops. Okay. So we may learn both of the methods in our in determine the safety for the finite slopes. Okay. So now we learn on the infinite slope. Okay. So we look on the definition first. Okay. Slope that extends for a relatively long distance and has a consistent subsurface profile that can be considered as infinite slopes. Okay. So that is for the first term. Okay. Normally infinite slopes, okay, we can imagine as a natural slopes, okay, where it doesn't have any what we call as top and toe, okay. Relatively, the surface length is greater than the height of the slopes. Okay. However, there will be another approach, okay, where uh, they they imagine that the failure plane parallel to the slope surface, okay, especially for the embankment field structure. Okay. So in this case, okay, we also can assume or we can use the approach, okay, under the infinite slopes. Okay. But normally, okay, for this finite slope, okay, because it has top and toe, okay, we use the normal method of slices. Or another approach, we use a linear type of approach, okay, where we assume that the failure was we assume that the failure will be fail in a linear failure plane, okay, not a circular or non-circular failure plane. Okay. Okay. So this is a slope surface, okay, where we assume that the sliding surface, okay, uh, where the height of the sliding surface is parallel to the slope surface. Okay, so in this case we call this as a H, okay, or D. Okay, so there we have a beta here. Okay, so this beta is the angle of the angle of the slope. Okay, so then the W is the width. Okay, so we may analyze only for one length. Okay, because we want to derive the equations. Okay, so we just concentrate on this L. Okay, so then the L of this one, so we can obtain the width, okay, by dividing the gamma, which is the unit weight of the soil, with the L and also the H. Okay. So the Wn, okay, is the normal stress acting on the sliding surface, while the Wp is the driving force, okay, which is acting on perpendicular to the parallel to the sliding surface. So this is perpendicular or in a normal conditions. Okay. Okay. So in terms, then we may derive the equations, okay, to determine the factor safety. Okay. So the W is the width. Okay. Then we can get the width for this block. Okay. Where unit width times L and times H. Okay. Okay, so then we get the width. Okay. So from the width, okay, we may work out to determine what will be the driving force and also the resisting force, or to get the shear stress and also the shear strength. Okay. Okay. So force perpendicular to the plane, okay, AB. Okay, where is the AB? Okay, this is the AB. Okay. So perpendicular is the NA. Okay. So then by using using the trigonometry, okay, so then we get W cos beta. Okay. So this is equal to W. This NA is equal to W cos beta. So this is beta. Okay. So then the W that we obtain here is gamma LH. So we need to multiply with W cos beta. Okay. So then force parallel to the plane, which is the AB, they call as a TA. Okay. So this is the TA, okay, where act as a driving force. Okay. Then we obtain W sine beta, or gamma LH cos beta. Sorry, there are some error here. Okay. Note that this is the force that tend to cause the slip along the plane. Okay. So okay. So this is this is not cos, this is sine. Okay. So I will change it first. Okay. Okay. So those the effective normal stress and the shear stress at the base of the slope element are, okay. So NA, okay, divide with the area of the base, okay, which is the L, okay. The L actually the length is not the length of the base, okay. So then they need to get this actual length. Okay, then from there you get L cos beta. Okay. Okay. So for the TA, okay. So TA over the area of the base, okay, gamma LH sine beta over L cos beta. So this is the formula, okay, to get for the stress, okay, where uh, W or NA or TA is the mass, is the weight, okay. So need to divide with the area to get the stress, okay. So then we obtain gamma H cos beta sine beta. Okay. So the reactions to the weight W is an equal and opposite force R. Okay. The normal and the tangential component of R with respect to the plane AB are okay. So there are another reaction force opposite for the NA and also for the TA. So they call as a NA and NR and TR. Okay. So then they get W cos beta and W sin beta. Okay. So for equilibrium, the resistive shear stress that develop at the base of the element is equal to TR, okay, over area of base, okay, which is the same approach from what we have discussed before. Okay, later on, the resistive shear stress also may be written as okay, TD over CD plus sigma tangent phi D. Okay. Okay. So uh, sorry. Okay. This part we have discussed previously. Okay. On the first step on the first discussion. Okay. So in order to what we call as to develop or to derive an equation. Okay. So the um, the TD, which is the shear stress, okay, is equal uh, to the what we call as to the TA or TR. Okay, okay, so equal to this tau. Okay, so from there, okay, so they get this kind of what we call as equation. Okay, which is the CD over gamma H equal to sine beta cos beta minus cos square beta tangent phi D, okay, which is equal to cos square beta times tangent beta minus tangent phi. Okay. So in order to replace, okay, the phi D, okay, and also the CD with the phi and C, okay. So we need to look again, okay, the derivation of the Fs based on the tangent phi over tangent phi D, okay, and also the Fs which is C over CD, okay. So in this case, okay, later on, okay, we may include, okay, this formula, okay, inside the above this approach, okay, and later on we may come out with this kind of equations, okay. So you need to try by your own, okay, how to get this formula, okay, based on these two formula. Okay. Okay. So you need to be creative. Okay. To replace, okay, the tangent phi D and tangent CD. Okay. in this formula, impose in this formula, and then later on you may get this kind of formula. Okay. But for me, I'm not prefer to use this kind of approach, okay, because this formula could not cater for the what we call as for the pore water pressure. Okay. Okay. We will discuss later on. Okay. Okay. So for granular soil, C phi equal to 0 and the Fs become equal to tangent phi over tangent beta. Those Fs is independent of the height and the slope is stable as long as beta less than phi e. So this what we call this statement. Okay, actually we have discussed on the previous slide. Okay, where beta, if the beta is less than the phi, so the factor safety is or the slope is considered as a safe conditions. Okay, so we have discussed previously. Okay, in here. Okay, okay. So okay, okay. So for instance, if the situation is on a granular type of soil, okay, where the C is equal to 0, okay. Normally, okay, when we carry out for a long-term analysis, okay, normally the C prime, okay, is near to 0, okay. So for example, if the soil, okay, is a mixed soil between cohesive and cohesiveless material, so by using the C prime, okay, effective stress approach, okay, the C prime normally near to 0, okay, so normally 5 to 10, okay. But if it is a granular type of material, consists of sand, okay, where it doesn't have any cohesive material, so the C become 0, and definitely, okay, the phi contribute on the factor safety value. Okay, so if a soil possesses cohesion and friction, okay, the depth of the plane along with the critical equilibrium occur may be determined as factor safety is equal to 1 and H equal to HCR. Okay, so for instance, if we want to build a slope at the factor safety is equal to 1, okay, so we should determine what is the HCR value. Okay, so HCR value actually when the factor safety, when what we call as when the shear strength equal to shear stress, okay, okay, based on the formula, both of the stress has H in their equation, okay. So then we need to put the H on the left side, okay, and the rest on the right side, okay. So then we can get the formula, okay, where HCR is equal to C over gamma times 1 over cos square beta times tangent beta minus tangent phi. Okay. So this is example, okay, on how to derive, okay, the equations, okay, when the H or when the factor safety is equal to 1. Okay. Okay. So 1 minus tangent phi over tangent beta, okay, where actually tangent phi over tangent beta is equal to 1. So from there, okay, they do the calculation, okay, to obtain, okay, the value and the equation for this HCR. Okay, so that's why the formula that we have discussed previously, okay, is only suitable for a slope where the groundwater is far below the failure surface. Okay. Okay, now we look on the stability of infinite slope. Okay, stability with seepage. Okay. So we will assume that there is a seepage through the soil and the groundwater level coincide with the ground surface. Okay. So we should make an assumption, okay, where the ground surface, or sorry, when the groundwater, okay, coincide with the ground surface. Okay. So the shear strength of the soil is given by tau equal to C plus sigma tangent phi. Okay. And for this case, okay, the W is in fully saturated condition. Okay. So then we need to use the gamma sat, okay, times LH. Okay. So later on, the NR is equal to gamma sat LH cos beta, while for the TR is equal to gamma sat LH sin beta. Okay. So the normal and the shear stress at the base are the same approach with what we have discussed before. The difference is only the gamma side, where the soil is fully saturated. Okay. So the resistive shear strength also could be given by, okay. So in this case, we need to add what we call as the pore water pressure. Okay. So mu is the height of the water in piezometer placed at F, okay, of surface, okay, times with the unit weight of water. So then they obtain H times gamma W. Okay. So later on, okay, by including the equation for the gamma W times H cos square beta, so they come up with this resisting force, okay, tau D is equal to C plus gamma prime H cos square beta tangent psi of D. Okay. So from this D tau D, okay, so then we may work out, okay, to determine what we call as the factor safety, okay, for the fully saturated slope conditions. Okay. So another limitation of this equation, okay, it's only suitable, okay, to be used to solve for the problem where the water is fully filled, okay, inside the slope. Okay. The first one without water, while the second one now when the soil is fully filled inside the slope. Okay. Okay. So later on, okay, how could we cater, okay, for the problems, okay, where the water level, okay, is less or below the slope surface, however, greater than the failure surface. Okay, so we may use the term of M. in our approach. Okay, the M actually is the ratio of the height of the water level to the slope failure over the total height, okay, which is we call as a Z. Okay, so for example, if the total height is 1 meter, okay, and the height of the water, okay, is 0.8 meter above the what we call as the failure surface, okay, so the M value is equal to 0.8, okay, because 0.8 divide with 1, okay, so then we may use the M equal to 0.8, okay, to cater or to calculate for the factor safety where the soil or where the water is below the slope surface. Okay. So this is a part of formula that we may use, okay, to solve or to determine the factor safety, okay, when the water is far is below the slope surface. Okay. Okay. Okay, the first approach, okay, we understand that the formula is only suitable, okay, when there are no pore water pressure or there are no water, okay, while the second equation, okay, has been restricted only for the soil or for the water at the ground surface, okay. So there will be another approach, okay, which is could cater for the soil and for the condition where the water is below the slope surface and above the failure surface, which is the M approach. Okay, so there is another approach, okay, where we use the raw or the actual equation, okay, and then later on we can choose, okay, which conditions or which situation that we can suit by using this formula. Okay, for example, if the water is um, below the slope surface, okay, then we use this approach, okay, the raw equation. Okay, so that's why for me, it's more easy to use this kind of approach rather than we use the equation that's already fixed. Okay, because actually the equation that I have discussed previously, okay, uh, I took from the uh, from the Raja and Das reference book. Okay, so however, the easy one that we may use, okay, for the infinite slope, actually by using the raw data or the raw equations. Okay. So for example, for this equation, okay, the shear strength along the failure plane, okay, which is the tau F, equal to C plus sigma minus nu times tangent phi. Okay, so the expression for the sigma, tau, and nu are, okay, so this is the sigma. Okay, so from there uh, we may put, okay, inside this equation later on, okay, or we can make our own calculation, okay, and then later on we may put inside this equation, okay. So while this is the for the tau m, okay, or in the previous equation, okay, this is referred to the shear stress. Okay. Uh, so for this case, okay, this is the driving force, while this is for the resisting force. Okay. So for the tau m, okay, as listed in this equation. Okay, so it is similar with the one that we have discussed previously. Okay, then for the new, okay, so we use the approach of the M, okay, times Z gamma W cos square times beta. Okay, so so uh, it it may rely on the value of the M. Okay, so the same goes to the sigma and also the tau M. Okay. Okay. So it is better to use this kind of approach rather than we use what we call as the fixed equations. Okay. Okay. So this is example a derivation for the fixed equation. Okay. So um, uh, for this case, okay. So we get the same approach, okay, with the one where the groundwater level, okay, or the water level at the slope surface, okay, as we have discussed previously. Okay, this one, okay, okay. So for this case, the M is equal to 1, okay. This is M equal to 1, okay. So for special case where C, okay, then for the case where the groundwater level at the surface while the C is equal to 0, so then the factor safety has been derived as gamma prime over gamma side tangent phi over tangent B here. So for the case where the whatever is far from below for the failure plane, which is M is equal to 0. So later on, while for the C, okay, it is similar for what we have discussed before, okay, where the phi is rely, where the factor is rely on the tangent phi over tangent beta. Okay. Okay. Note that when the C is equal to 0, the factor safety is independent of the height of the slope. Okay. The slope will be stable as long as the slope angle beta is less than the friction angle. Okay. If both cohesion and angle of internal friction angle is not 0, then the critical condition Fs equal to 1 will be achieved when Z, okay, which is the Z or ZCR is the critical height. Okay. So for our total stress analysis, the shear strength parameter Cu and the phi u are used with a 0 value of M. Okay, for total stress, we may not consider the pore water pressure, so there will be no value for the for the M. Okay. Okay. So that is how the derivation for the infinite slope factor safety value. Okay. So we may discuss in terms of some example, okay, on how to determine the factor safety, okay, by using all of this approach. Okay. So we should have a break for 10 minutes and then we may continue with some of example. Okay, at the moment, I did not upload any example in the e-learning. Yeah, I will upload later on after we do some discussions on the example. Okay, so we take a rest. Okay. I know it's very hard to understand without doing any calculation uh, based on an example. Okay, because the first half lecture is more related to the equations on derivation of the equation. And we may discuss on the example after we break. Okay, so we break for 10 minutes. So we may start around 3 past 3, Okay.
Excuse me, Prof.
Sorry?
Excuse me, Prof. I am Hamid. I
Okay.
would like to talk with you 1 minute, if you like.
Can we discuss after class, Hamid?
No, just I have a little problem with my e-learning just now.
Oh, okay. Hamid, I will text with you, Hamid, because you need to send a message
Yeah.
to the postgraduate staff. Okay?
Thank you so much.
Okay.
Because I attended my subject is not uploaded in my e-learning. That's right.
Okay. Don't worry, Hamid. We will try to solve it.
Yeah.
Okay?
Thank
Okay,
you
take
so
a rest
much.
first, Hamid.
Thank you so much.
Okay?
Thank you so much, Prof.
Hamid. Okay. So we continue with several examples. Okay. So I will share with you this note. Okay. This example. Actually, I got it from Dr. Noli Gofa textbook. Okay. For this example, okay, where she used the M approach, okay, where we have discussed previously. Okay, so yeah, what we have discussed previously, the derivations of the equations, okay, for the M approach, okay, has been listed in this example. Okay, okay. Wait. I have a delivery. Wait a minute. Okay. So yeah, the same that we have discussed previously. Okay. So this is the simplified one. Okay, where the water is fully uh, full. Okay, up to the slope surface. Okay. So the same discussion that I have discussed with you. Okay. So now we may look on the what we call as on some of example. Okay, which is related to the approach, which is on the M approach. Okay. Okay. So for the first one, example problem number 5.1. Okay. Along natural slope in a fissure of a consolidated clay is inclined at 12 degree, okay, to the horizontal. The water table is roughly at the surface of the slope. Okay. At a slip has developed on a parallel plane to the surface at the depth of 5 meter. Okay. So the saturated unit of the clay is 20 kilonewton per meter cube, and the peak strength parameter are 10 for C and 26 for the phi value. Okay. Determine the factor safety along the slip plane. Okay, now the informations that been provided is the beta, which is 12. Z, the depth of the slope is 5 meter. Okay. In this case, okay, as I told you previously, okay, where we have what we call as the ratio between the groundwater, the height of the groundwater and the height of the slope. Okay. So in this case, due to the water is at the surface of the slope, okay, so we assume that the groundwater is 5 meter high, okay, and the Z is equal to 5. So 5 over 5 is equal to M is equal to 1. Okay. So then it is a fully saturated, okay, where gamma sat is equal to 20, C is equal to 10, while the phi is equal to 26. Okay. So based on the formula, okay, first we may count for the sigma. Okay. So 1 minus 1, okay, gamma plus gamma saturated. So we times Z cos square beta. Okay, then we obtain 95.5. Okay. So we may eliminate this one because 1 minus 1. So M1 times saturated times Z cos square times beta. Okay, so that is for the sigma. Okay, while for the tau m, okay, which is the shear, which is the shear stress. Okay, so so we may eliminate this one. Okay, 1 times gamma sat z sine beta cos beta, then we obtain 20.3. Okay. So later on, okay, by including the pore water pressure, okay, so m times z gamma cos square beta, so we obtain 46.8. Okay, so for the shear strength, okay, C plus sigma minus minus pore water pressure tangent phi. Okay, later on we obtain the tau F is equal to 33.8. Okay, so by dividing 33.8 with 20.3, okay, so the value for the the value for the factor safety for this case is equal to 1.66. Okay, so that is example, okay, by using the M approach. Okay, however, it is a straightforward, okay, because we use the M is equal to 1. Okay, later on we may try this approach to another to another example. Okay, so then we obtain 1.66. Okay, now, okay, how about we use this formula? Okay. So I want you to involve, okay, to 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 calculate the factor safety, okay, based on 5.7 equation. Okay, can you get 1.66 as well? Okay, okay. First you need to list all of this input. Okay, okay. So I want you to make some calculation, okay, and then can we get 1.66 as well by using the formula derived in equation 5.7. Okay. Okay. So write down first this one. Okay. So we need to spend not more than 5 minutes. Okay. Okay. So make sure that you have a calculator. So the beta is 12. Okay. Z is 5 meter. Okay. Or the water is fully saturated. The ground is fully saturated. M is equal to 1. Saturated unit weight is 20. C is 10. Y phi is 26. Okay. Okay. So are you ready?
Yes.
Okay. So then we use the equation in for 5.7. Okay. We try to get the value or get the safety value. Saturated Z cos square beta sine beta plus pi over saturated tangent beta. Okay. Try to get the calculation first. And so good. 20. Okay, you may use unit weight of water 10 or 9.81.
Oh, dua-dua boleh tak?
Ha? Boleh. Ha.
Oh,
Tapi
okay.
nak mudah guna 10. Cuba guna 10.
Oh, okay.
10.
Doctor, is it
So
one?
I get 1.65. Okay. So what's your answer? 1.65.
No, 1.19.
1.19.
19.
How come you get 1.119?
1.25 tak?
1.65.
65.
Okay. Most probably you do you need to the gamma effective is actually 20 minus 10. Okay. While the C we can use the C prime. C prime is what we call as C prime is equal to 10. Okay. So saturated 20 times Z is equal to 5. Okay. Times cos. Cos square actually cos 12 cos 12 sin 12. Okay. So on this part I obtain 0.502. Okay. 0.502. Okay. While for this part, okay, which is 10, 20 minus 10, okay, 10, tangent C26, okay, over 20 tangent beta, so beta is 12. So for this part, I obtain 1.14, okay. So plus 0.502, so I obtain 1.65. Okay.
Yang cos squared tu
Ah,
tak beta sin beta je yang squared ke sekali semua sekali?
maknanya cos square beta times sin beta.
Oh, okay. Patut. Okay.
Ah.
Ingatkan dalam tu. Okay.
If
My
we are using
result
the
is 1.6. My result is 1.65000.
yes. Okay. 1.65 kan lebih kurang kan. Okay, I guess to get more accurate with 1.66 might be you need to use the gamma water to 9.81. Okay, because if you use 10,
because I use it 10 actually. Maybe
okay.
if I use 9.
Okay, so that is the limitation of 5.7. Okay, where it only could able to determine the stability if the water level at the slope surface. Okay. However, actually the M approach is very powerful, but for this example, okay, because they put the water is on the ground surface. Okay. So we may use this approach for another example later on. Okay. Okay. So can we move to another example? Actually, we try to finish at 4. Okay, any question?
Doktor.
Okay. Okay. Okay, so this is another example, okay, where I use Dr. Kamaruddin reference book. Okay. Where for this example, okay, so we use the what we call as the raw data, the raw equations, okay, on to derive the factor safety. Okay, so again, it is more easy to understand the concept of the shear stress and also the shear strength. So please, can you please mute your microphone? Okay. So I will share with you the example because I could not share for the full textbook because actually Dr. Kamaruddin, okay, sell it in the hard copy. Okay. Okay. So the same approach with the the M approach, okay, where we may derive the equation for the sigma and then get the tau, okay. So this tau is the shear stress, while this is the shear strength, okay. So then we may include the sigma in the equation of 3.3, okay. Okay, in this example, Dr. Kamaruddin has divided into 4 situations here, where for the first 3.1 to 3.4, it is suitable to be used for a cohesive type of material, okay, where they have C and definitely they have phi value. Okay, so when it okay, so this is cohesive soil without seepage, without any groundwater level there. Okay. So when there is a seepage, okay, which is parallel to the slope surface, okay, either it is up to the ground level or it is between the ground level to the failure surface. So we can use this approach. Okay. So 3.5 is the pore water pressure, okay. While for the 3.6 is the shear stress, okay. So actually, for the shear stress, okay, we may not use the effective stress value for the to derive to get the tau, okay, because the water doesn't uh, have has an ability to shear, okay. So that's why we not we just include the water in the calculation of the tau, okay. While for the shear strength, okay, so we may use the effective stress approach, okay, where C prime and sigma prime tangent phi to calculate for the S prime. Okay. Okay, for the granular soil with seepage, okay, it is similar with the 3.5 and 3.6. Okay, this is with seepage. However, there is no C value, okay, because it is a granular type of soil. Okay. Then the factor safety, the derivation is still similar, okay, with 3.8. Okay, while for the granular soil without seepage, okay, 3.1, 3.2 is similar. However, it doesn't have any pore water pressure. Okay, so we just multiply sigma with tangent phi, okay, without including the water. Okay, then we obtain 3.4 to get the factor safety. Okay, so now we look on the example. Okay. So this is an example. Okay. For the infinite slope where the groundwater level is far below the slope surface. Okay, calculate the developed shear strength and shear stress along the failure surface. Okay. So the developed shear stress can be determined using the equation 3.3 and 3.1 because there are no seepage and also it is a cohesive soil with where they have C and P value. Okay. And then we just put the equation, put the input inside the equation. Here later on we obtain 43.4. Okay. So that is for the S. Okay. While for the shear stress, okay, by using the equation in 3.2, okay, then we just include all the input, then later on we obtain 15.4. Okay. So the question doesn't require us to calculate for the factor safety. Okay. So that's only the answer that that we have obtained for the S and tau. Okay. So for example, if you want to get the factor safety, 43.4 divided with 15.4, so we obtain 2.82. Okay, the factor safety is equal to 2.82. Okay. Okay. Okay, so for this example, okay, it has three sub question. Okay, for the first one, determine the safety factor against sliding, assuming the interface friction angle between the sliding and the stationary subsurface subsoil, stationary subsoil is 20. Okay, so this is the internal friction angle. So phi is equal to 20. So the depth is 6 meter. And then unit weight 17 C30 and the angle of the slope is 25. Okay. So first, the same approach that we may calculate first for the S and then get the tau. Okay. And then later on S over tau is equal to 1.5. Okay. Okay. So determine the critical height of the slope. Okay. So, okay, we may use the equation that we have discussed before, and then we also may use this, the data, or sorry, the equation from the S equal to tau, okay, to get the critical height of the slope. Okay, so the equation that we have discussed previously, okay, which is this one, okay, so then can we get the same answer, okay, for both for these problems? Okay, so we look on the B first. Okay, so critical height of the cohesive soil can be determined by taking the factor of safety equal to unity, which is factor safety equal to 1. Those equating equation 3.3 to 3.2, okay, which is this is the S, okay, while this is the tau, okay. Then both of the equation have the H value or the H parameter on the left and also on the right. Okay. So then we need to rearrange, okay, and later on the equations after the rearranging, so the equation will be like this. Okay. So the C, okay, is equal to gamma cos I times sin I minus cos I tangent phi. Okay. So when we calculate it, okay, 30 over 17 cos 25 times sin 25 minus cos 25 tangent 20. So the value is equal to 21. Okay. So now we try to use this equation. Okay. Can we get the same answer with the one that we have discussed in this part? Okay. So if C is equal to 30, okay. Unit weight, in this case, unit weight, because the water is far, so unit weight is equal to 17. Okay. So cost, okay, cost 25. Okay. In this case, cost 25. Tangent, what is the fee? Tangent 10. Tangent, tangent 20. Okay. So does the answer is similar or not? Okay, let me try. 30 minus 17, okay, time cos beta is 25, cos 25, tangent phi is equal to 20. Okay. So 5.9. Okay. So I guess this is only suitable when the water is on the surface. Okay. We try to look for another example, not this one. Okay. So this is not suitable to be used to get the Z. Okay. So we need to look on the slide that I have discussed previously. Okay. Let me look on the slide first. Z. Okay, this one. I need to stop. Okay. Okay. So this is the equation. I guess this equation will provide the same value. Okay. So when the water is far from the slope, so we can use this equation directly, okay, to get what is the HCR or the critical height. Okay. So for example, the C is equal to 30, okay, over 17. 17 is the unit weight. Okay, 30 over 17. Okay. Cos square beta is equal to 20. Okay. Sorry, beta is equal to 25. Okay. Times tangent 25 minus tangent 20. Okay. So we try to, I guess it is similar with the equation derived in Dr. Kamarudin example. Okay. 30 over 17 cos 25 times tangent 25 minus tangent 20. So the answer is 20.99. Okay.
Yes, doctor. 20.99.
Okay. So okay, this equation is suitable when the groundwater is far, okay, from the surface. Okay, while there is another equation, okay, from Dr. Noli reference, where I have not discussed in this slide, where when the groundwater level is on the slope surface, okay, so then we can get the value for the HCR. Okay. Okay. So this equation is only for when the groundwater level is on the surface. Okay. Okay. So meaning that for me, it's better to not rely on the simplified equation. Okay. So it's better for us to use the raw equation from the S and tau and then get the effective safety. Okay, so that is much more easy, and also we may understand better. Okay. So then we look on the last case. Okay. Okay. So the C, okay, determine the safety factor against sliding if the groundwater table is at 2 meters below the slope surface and the seepage occur. Okay. So it is 2 meters, means that the height of the water is 4 meters. Okay. Use the saturated unit weight of soil, gamma saturated equal to 19, and assume other parameter are unchanged. Okay. So when we look on the solution for the C, okay, okay, before that, okay, when we want to use the approach of M, okay, so the M value is the ratio of the height of the water. Okay, for this case, the height of the water from the failure surface is 4 over the total height of the slope. So the total height of the slope is 6. So 4 over 6 is equal to 0.67. 0.67. Okay. So that is the height of that is the M value. Okay. Okay. We may discuss later on the M approach. Okay. Because when we look on Dr. Kamaruddin approach, he has divided into 4 type of situations, which is cohesive without seepage, cohesive without seepage, cohesive with seepage, granular without seepage, granular with seepage. Okay. However, when we use the approach on the M, so we can use it is a universal equation, okay, and it could cater for different type of situation. Okay, so that's why the M is for me is more powerful, but we need to understand how to use the M approach. Okay, however, for Dr. Kamaruddin is useful, okay, when we want to understand in terms of how to get the factor safety, okay, for the infinite slope based on S and tau. Okay. Okay. So then we have a S, okay, and then for the S later on we need to calculate for the sigma due to the different what we call as soil properties. Okay. Because 17 times 2, okay, the 2 is without any water, 2 meter near to the surface is it is under a normal unit weight or bulk unit weight, okay, while for the 4 meter below, the 4 meter below, it is within a saturated condition. Okay. So 19 minus 10 times 4. So this is equal to 17 for the sigma. Okay. So then for the S, okay, we obtain 50.93. Okay. So that is for the S. Okay. So for the tau, okay, since water cannot resist shear stress, okay, so then there are no need for us to use the effective stress. Okay. So the effective stress approach only for the compressive situation. Okay. So reader may refer to another reference for the derivation. Actually, for the M approach, okay, when we look on the M approach, the tau also we use the saturated. Okay, wait, tau. Okay, this one. Okay, so they also use the saturated. They not use the effective. Let me find. Okay, for this tau set H C cos sin O2. For the S, where is the theta saturated? Okay. Okay, because for the S, okay, actually they use the effective, okay, because the sigma will minus with the mu, okay. However, for the tau, okay, so they use the saturated, okay, because it's not been divided with the any what we call as any pore water pressure. Okay. So since water cannot resist shear stress, so they only use the saturated, gamma saturated. Okay. Then the tau is equal to 42.13. Okay, from the equation 3.4, S over tau is equal to 1.21. Okay, so that is for the approach or the methods from Dr. Kamarudin textbook. Okay, so now we may use the equation in for the M. Okay, so as we have discussed before, M is equal to 0.67. Okay, so now we try to solve the problem. Okay, by using the M approach. Okay, so you need to write down first the what we call as the property of the equation. Property of the material. Okay. So for the example of C, okay, the unit weight is equal to 17. Okay. The C is equal to 30, while the phi is equal to 20. The beta is equal to 25. Okay. Then the unit weight saturated is equal to 19. Okay. So we may use the equation of M to solve this problem. Okay. So for example, for the sigma, okay, for the sigma, okay, so you need to do along with me, okay, to get the value for the practice safety. Okay, so we use this equation. Okay, so 1 minus our M is 0.67, okay, times with the saturate, time with the effective stress, time with the 17, okay, plus 0.67 time with 19. Okay, 19 is the saturated. Okay, so then times with Z. Z is equal to 6 meter. See, Z is 6 meter. Okay, Z is 6 meter. Okay, 6 meter. Okay, cos square. So the beta is 25. So does it have the same value, okay, with the example from Dr. Kamarudin? Okay, so in Dr. Kamarudin, the sigma is sigma. So Dr. Kamarudin just can get the S directly. So we calculate first for the sigma. Okay. So the sigma is equal to 1 minus 0.67 times 17. Okay. Sorry. 1 minus 0.67 times 17. Okay. Plus 0.67 times 19. Okay. So we obtain 18.34 times 6 times cos 25 cos 25. Okay, so the value for the sigma is 90.4. Okay, so that is for sigma. Okay, then for the tau m, okay, so 1 minus 0.65, 67, sorry, 0.33 times 17 plus 0.67 times 19, okay, times z is equal to 6 times sine 25 cos 25. Okay, so tau m should be 0.33 times 70 plus 0.67 times 18.34 times 6 times sine 25 times cos 25. So we obtain 42.1, 42.15. Okay. So for the tau m, Dr. Kamarudin, okay, 42.13, we obtain 42.15. Okay. So the last one is the new, okay. So for the new, the pore water pressure, so M is equal to 0.67 times Z 6 meter times 10 times cos square beta. So the value is 0.67 times 6 times 10 times cos beta is equal to 25 cos 25. Okay. So the value of mu is 33.0. Okay. So the last one is the tau f, okay, where the C is equal to 30 plus 90.4 is the sigma minus 33.0 tangent the phi is equal to 20. Okay. So 90.4 minus 33, okay, times tangent 20, okay, times 30. So 50.89. Okay. So the factor safety is tau f over tau m. 50.89 divided with 42.15, 1.20. Okay. Okay, so same. Okay, Dr. Kamarudin 1.21, and then for our calculation is 1.207 or 1.21. Okay. So at least you know how to use the M approach, and you can use what the direct equation, the equation from Dr. Kamarudin. Okay. And when the situations where the water level is far, okay, we can use the simplified approach. Okay, or where the groundwater level is on the surface, we also can use the simplified approach. Okay, so I guess that is for for the infinite slope. Okay, so actually this approach is very useful. Okay, when we want to analyze for a global area. Okay, because this formula is could be used to solve the problem where we want to use the GIS methods. Okay, so for the method of slices is not suitable to be used for a global global approach. Okay, it's only for localized. But for this equation, okay, we can use it to solve or to determine the area, a global area by using the GIS approach. Okay. However, I'll not discuss in our syllabus because one of my I have a student where they use this equation, okay, to determine the factor safety, okay, for a huge area, okay, by using the GIS concept. Okay. Okay. So I guess that's all for today. Okay. Hamid. So you can wait for a while, Hamid.
Yes. I'm
Congratulations
ready.
on your e-learning. Okay. So any question before we end?
Lihat ada.
Excuse me, Prof, can you share these examples on e-learning?
Yes. I will share some of the example in the e-learning. Okay.
Thank you very much.
You're welcome. Okay, so that's all for today. So Hamid, just wait, Hamid. We have a short
Yes.
discussion. Okay, so that's all for today. I will share the recorded version later on. Okay, so Assalamualaikum and until we meet next meeting.
Salam.